Check it out now, y'all.
NanoHub U, online instruction.
Hi, and welcome to the course called Physics 342. This is a course which is an introduction to modern physics. And in particular, it's an introduction to modern physics for engineers. So we're trying a new format this semester. We're giving the lectures to you in advance. And then we're going to, of course, meet in class and discuss these lectures. So we hope this new format will improve your understanding of this very interesting topic. The first lecture today is sort of a historical overview of the course. And I'd like to begin by telling you that the real storyline is this, it's really the amazing story of quantum mechanics. Quantum physics basically underlies nearly every major technical innovation of the past century. And this course is about understanding the development of quantum physics and developing appreciation for the amazing predictions that have resulted from this field of study. I found this comic book cover on the web, and I thought I'd reproduce it here as an introduction to the course. You can see the title of the comic book is The Amazing Story of Quantum Mechanics. It's called A Math-Free Exploration of Science That Made Our World Today. The only correction that I have to make is that this course is not math-free. It's pretty intensive mathematically, and if you're allergic to math, you may consider not taking this course at this point in time. The course will tell you, as we develop topics in the course, we're going to learn about things that on the face of it seem very improbable. So if you haven't heard something strange in one of these lectures, then it must not have been a very good lecture, because quantum mechanics truly is a subject that makes incredible predictions, and of course all these predictions that we'll talk about during the course of the semester have been verified experimentally. So I'm not going to spend time speculating on how things might be. The course is very closely tied to experiment, and I think you'll see that as we go through topics. By way of motivation, since this is a course basically for undergraduate engineers, I go to the U.S. National Academy of Engineering Grand Challenges. So these are the top 14 problems that the best engineers in the United States have identified as truly difficult problems that must be solved in order for our society to continue progressing. And what I note is that fully half of these topics will require some understanding of modern physics, some understanding of quantum physics in order to make progress. Many of these problems will also require a transdisciplinary effort on your part, which means that if you are just an expert in one topic, you're probably not going to be able to make significant advances in solving these problems. These problems are so complicated that they require information and knowledge from a number of different topics. And that information and knowledge has to be synthesized in a uniform way in order for you to work on these types of these problems. So if you take these issues as drivers for jobs in the U.S. in the future, I think it's important for you to develop some understanding of quantum physics, because roughly 50% of these problems will require some quantum physics in order to solve them. As a way of introducing the course, I'd like to provide some historical perspective. And I want to say that most of the physics that you've studied in your introductory physics courses has basically been discovered and developed between roughly 1600 and the mid-1800s. And the reason these topics of mechanics, magnetism, optics, electricity, thermodynamics, the reason these topics have been developed is because they were essentially required to correct some of the theories that Aristotle and his buddies put forward back in ancient Greece. And I'll try to emphasize that a little bit in the next slide. The problem is that the ancient philosophers basically had this attitude that if you just think about a problem, you can basically solve it by developing some logical framework. And if your framework was more logical than somebody else's, then your framework survived. And this viewpoint, of course, met with great success when Euclid developed his elements of geometry. These elements are basically a series of theorems and postulates, each of which can be proved and each of which leads to another understanding of plane geometry. The trouble with this approach is that it gives rise to a culture in which only a few people know the accepted answers, and they have to then dispense that information and that knowledge to others who are trying to understand how the world works. And that whenever you get a situation like that, in my experience, it's not a very healthy situation. And of course, this rise of science was basically driven by the need to overcome a lot of these misconceptions that Aristotle had developed. So just to summarize briefly some of Aristotle's dubious results regarding science, right? Aristotle thought the earth was at the center of the universe. That's clearly incorrect. He thought there were only 4 elements, and those 4 elements were earth, air, water, and fire. And he thought that everything that you see on earth could be created from anything else just by shifting the relative amounts of these 4 elements. Well, we know that's not true because there's 130 some elements now that are chemical elements that have been discovered, and the 4 that Aristotle put forward have nothing to do with what we see. Aristotle thought that a vacuum was impossible, and he used this impossibility of a vacuum to argue against atoms, the existence of atoms. He thought time was immutable, and this, of course, was recently challenged in the early 1900s by Einstein's theory of relativity. That's a topic that we'll discuss this semester. So there's many of these examples. I just list a few here, and it's looking back, it's kind of interesting to ask, why did it take centuries to overcome these misconceptions? And the answer actually is kind of interesting. It's just that very often the way nature works has really little to do with common sense. And what you have to do is you have to go out, you have to do an experiment, find out how nature works, and then you have to develop a theory to fit the experiment. And Aristotle was not an experimentalist. He just liked to sit and think and develop logical frameworks. And whenever you do that, you're going to run into some problems. So one of the prime examples of how Aristotle's theory of motion was corrected was that in roughly 1620s, this guy Galileo starts scientific revolution by measuring the way objects moved under the influence of gravity. He found that his experiments completely contradicted Galileo's results. And within 65 years of his work, Newton's Principia is published, right? And Newton was the first person to actually develop a comprehensive theory of motion. This theory of motion dominated scientific thought until about 1750, when a new topic called electricity became fashionable. And it took about 100 years of hard work from scientists all over the world to basically establish the fundamental laws of electricity and magnetism. And with these understandings of how electric and magnetic fields worked and how electric and magnetic phenomenon behaved, there was an attempt to unify both electricity and magnetism by Maxwell in 1864. And this unification led to a rather dramatic development called electromagnetic radiation, right, or electromagnetic waves. So this prediction of electromagnetic waves was something that was completely unexpected. It just developed from the understanding of electricity and magnetism separately. When these two topics were combined, this prediction of electromagnetic waves emerged. So there are many examples of how these electromagnetic waves interact with matter, and these experiments were done in the late 1800s, the early 1900s, and the results were extremely confusing. So even though everybody believed by the late 1800s that they understood Maxwell's predictions about electromagnetic waves and they thought they had developed a comprehensive theory of electromagnetic waves, when those EM waves started to interact with matter, the results couldn't be explained using conventional theories. So all these topics, or all these experiments led to contradictions of a very fundamental nature, and all these topics are of fundamental interest to this course, and we're going to click through a lot of these during the course of the semester and try to explain the way the quantum mechanics and the modern theory of the atom allow you to understand the experimental results. It's useful to provide an overview of where this course is going to take you, and I like to use this broad overview that this website Hyperphysics gives. So I list the website down here for you to look at. I refer to it often during the semester. It's a very useful website to go to and get some information about a particular topic. And what I really like about it is it shows how different topics are all interconnected. So if you go to their website for quantum physics, you'll see this organization, and a lot of the topics that are listed here will be covered during the course of the semester. So if you have a chance, go take a look at it and learn how to use it, because it does provide a lot of useful information in a very simple and integrated way. I mentioned up front that this course will involve mathematics, and I think it's important that I mention the type of mathematics that we'll use. In my mind, there are four types of mathematics. One is called a functional relationship. These are just simple equations that relate experimental parameters to observables, right, and allow you to predict certain things. So this is basically algebra, right? We're going to definitely make use of that. We're going to use differential equations. So a lot of the work we're going to do is based on dynamical models of how electrons move. And what we're going to find is that those dynamical models involve differential equations. So there will be a strong emphasis on differential equations in the course. Most of the solutions for the differential equations will be given to you, so you don't actually have to solve the differential equation, but you have to know what the solutions mean, and you have to know what the predictions of the solutions are. There's in the middle of the course, there's a fair amount of work on probabilistic models. So here we're going to talk about probabilities and probability distributions. And this will allow us to go from classical statistics to quantum statistics. And so the way of thinking about things in a probabilistic way is important. And then lastly, we're going to discuss electromagnetic fields. So there's going to be some discussion about electromagnetic field equations, which means that you have to have some familiarity with vectors and vector operations. So all four of these levels of mathematics will be used. This course is not a survey course. It's not an easy breezy course that provides an overview of modern physics. We actually get involved in solving the important equations and interpreting what the solutions mean. So if you're looking for this overview, this easy breezy overview, this is not the course for you. How to get the most from this course? Well, I always put this in on every class I teach at Purdue. I try to emphasize to students important aspects of the course so that they know from day one what to expect. You can read this through on your own. I'll just pick out a few that I like to emphasize. One of the points is that you have to realize from day one, that is from today, that this is not a recreational course. You will really need to work at it. You have to develop a schedule to view these taped lectures, and you'll have to force yourself to take notes. It's very important that you leave every lecture with a question, and there'll be ample opportunity for you to ask those questions, and we can discuss them in a group format. This is an important way to learn new material. It's important for you to work through many simple problems. I call these confidence building questions. One of the best ways to convince yourself that you understand material is to be able to devise a simple problem and then go about solving it. There will be homework problems involved in the course. The homework problems are a little bit more involved, it's important for you to understand the solutions and study those solutions so that you know the type of calculations that are required for problems in quantum physics. Don't fall into the trap that you just have to find a formula to plug into. This course is definitely more about understanding the broad framework of how things are put together. So it's not a course about formulas, it's more a course about how to think about modern physics. I encourage you to read many textbooks in parallel, and I also have to recite this last point here, right, which basically says that in contrast to engineering and physics, it's legal to be interested in something just because it's interesting. So more than a few of these topics we're going to discuss are just interesting topics, and the development of these topics and the solutions of these problems have led to advances in technology, which engineers have certainly played an important role, but the early work involved was not necessarily closely tied to a device. It was just an interesting thing to think about at the time. How best to learn this material? That's a very important question that should be discussed in any course that you take. And in my opinion, there's three ways that you have to learn, three things that you have to do in order to learn this material, right? First of all, you have to read about it. That means you have to go to textbooks, you have to go to websites, and you have to read the words and try to understand the development of the subjects. Secondly, you have to listen to somebody discuss it. So you can listen to my videos. You can come to class for class discussions. There's a huge number of supplementary material on YouTube that's available. A lot of it is really very good. So you have to listen to someone talk about it in order to learn how the vocabulary is used. And then the third thing that you have to do is you have to work as many problems as you possibly can. You have to do the homework plus more, because it's only in the process of actually trying to solve a problem that you really understand what you know and what you don't know. I will mention that a common theme that the best students I have taught at Purdue have told me over the years. I sometimes get to know a student who's done very well in a course, and at the end of a semester I'll ask them, well, like, what's the secret? What's your secret for success? Because you happen to do very well in this particular course. And inevitably they come back with a statement that can be written as, well, we reorganize your lectures in words that make sense to me. So these good students somehow take the material that I provide, take the material that they read in textbooks, and they reorganize it so it makes sense to them. And historically, I found that those tend to be the top students in any particular class. So that's a common theme, and I encourage you to try to rework the lecture notes in your own way so that you can better understand the material. What are your responsibilities? Well, I find it important to to provide a list of things that I expect you to do. I'm not going to read through all the items in this list, but I will tell you that if you do not keep up with the video lectures, you're gonna be in trouble, right? So you don't fall behind. You have to set up some schedule and you have to stick to it. There's about 6 25-minute lectures a week. Some are a little bit shorter than 25 minutes. Some are a little bit longer than 25 minutes. Sometimes we don't do a full 6 lectures in a given week, but you've got to keep up with those lecture courses. You have to know the contents of the syllabus, so you have to understand what we're trying to accomplish and where we're trying to go. You have to leave sufficient time for you to work and acquire the background knowledge that's required to understand this material. Right? The vocabulary is different. The way we think in quantum terms is different than what you've learned in your study of classical physics or even in engineering physics. And so you have to make an effort to understand the vocabulary and know what the words mean. Right? So please look through this list. It gives a number of helpful suggestions that I hope you'll follow. And I hope you refer to it throughout the semester so that it's clear to you what I'm expecting you to do in order to keep up with this course. Lastly, I will say that because there are some long-winded mathematical derivations in this course, I tend not to emphasize that during the lectures. Instead, I tend to put the mathematical details at the end of a lecture in an appendix. So a lot of times when I get to a certain point, I'll just put in the lecture notes, see the appendix for the details. The answer that you get is this, okay? And I just provide the answer. That's the thing that you've got to remember. That's the thing that you've got to know how to work with. But if you want to know how we got that answer, then it's up to you to check the appendix and work through the math on your own, right? All the details are there. It's so it shouldn't require a tremendous amount of time, but you can gain a very good appreciation for what's involved by working through the math details. So that's the end of the first lecture. The second lecture, we're going to discuss we're going to try to set up a discussion that compares and contrasts the behavior of particles and the physics that's been devised to describe particle motion with the properties of waves and the physics that's been devised to describe wave motion. So the second lecture will be about particles and waves. So thanks a lot, and best of luck during the semester.